Okay, so for the definitions, it says define the following terms. Hygroscopic, I'm sorry, I just called it something else. It's hygroscopic. And doesn't that sound like you're looking at something? Scopic? Yeah. You know? Hygroscopic is that it readily absorbs moisture. And then the limiting reactant is the reactant you run out of first. That's all you have to say. Just make sure you do all your work from it. Okay, and that does limit your product. You knew that though. Number 2, how many molecules are in a mole? You have this memorized. 6.02 times 10 to the 23rd. You just memorize it. That's it. Just put it in your brain. Then number 3, it says how many atoms are in 58.93 grams of cobalt? Now immediately I went and figured out how many moles of cobalt that was so that I could figure out how many atoms it was. And when I did it, I figured out that's 1 mole of cobalt. Did you guys like know that, or did you figure it out too? I immediately went to figure out how many moles it was. So anyway, you may want to look before you is what I'm saying. But if you looked, you notice that that is how much cobalt weighs. It's its gram atomic weight. And so that means there's 6.02 times 10 to the 23rd atoms in 58.93 grams of cobalt. Okay. Really? Am I the only one that figured out how many moles that was? You did it too. Okay, good. Because you know what if it wasn't the amount of moles? You had to figure it out to get started. So I'm there. I'm with you. All right, number 4. Indicate how many moles are contained in each of the following samples. I think we have time, so let's try. Okay. So we have 100 grams of iron. We want to know how many moles. 100.0 grams times line, grams of iron, because this goes here, moles of iron. We know in 1 mole, and we look at the chart, and it gives us 55.85. This will cancel. We have 4 significant figures both places, so our answer is going to be 1.791 moles of iron. Really sorry about the board. Okay, the next one, 250 grams of methane times line. Grams of methane go down here. Moles of methane go up here. I can do this. 1 mole. Now we're going to go in, Andrew, and we're going to count it. 4 times hydrogen, which is 1.01, so it's going to be 4.04, plus 12, so it's going to be 16.04. Did I do that right, guys? I hate doing them in my head. And that's going to give us 4 significant figures, 15.58 moles of methane. Okay? And then the last one it gives us there, the last one it gives us is 500 grams of potassium iodate. Oh, that's a fun word. They sound like they're dying down there, don't they? Okay, grams of potassium iodate, moles of potassium iodate. 1 mole, it does. And then you're going to add that up. It's going to end up being 214, it's heavy, 214.00. So, wow, our answer is going to have 4 significant figures. So it's going to be 2.336 moles of potassium iodate. Okay, so far so good? Yeah, number 5, you're just going to do the opposite, aren't you? You're going to go from moles to grams. Determine the mass of each of the samples below. So the first one we have 14.5 moles. We're going the other way now of strontium times line. That's an R. Okay, we know this goes down here, so moles of strontium and grams of strontium is what we're looking for because we were asked for the mass. And so you're going to go on your chart and find strontium, and it is a group 2 metal. Number 38 is the atomic number. And so strontium is 87.62 grams for every mole of strontium. And so you're going to answer in 3 significant figures because your original number was in 3 significant figures. And so the answer is going, it's actually 1,270. And let's go ahead and do this one. We have 14.5 times 87.62 equals, what comes out in my calculator, but you have to have 3 significant figures, 1, 2, 3. So I'm going to get rid of everything here, and that 0 is not a significant figure, it's a placeholder, because this could actually be written as this, couldn't it? And so either way, that would have 3 significant figures, and you have to have grams of strontium. So we're just going the other way now. In the last problem, we went from the mass to the moles. Now we're going from the moles to the mass. On B, calcium sulfide. So we're going to put our moles of calcium sulfide. Here we're going to put our grams of calcium sulfide. To every 1 mole, you're going to look in your chart. Calcium is 40.08. Sulfur is 32.06. Okay, so I'm going to show you, just because we're just getting started with this. So the calcium is 40.08 grams, and because there's just the 2 of them, I'm going to put them up and down on this one. 32.06 grams, so that's going to give us 72.14 grams. Put it up here. We have 2 significant figures we're starting with, so we have to end with 2 significant figures. And so in this case, the answer is going to be 3.2 grams of calcium sulfide. 3.2. On C, we have 0.876 moles of magnesium sulfate. Okay, so we have moles of magnesium sulfate down here. We have grams of magnesium sulfate up here, 1 mole. So you're going to go look. Magnesium is group 2. It is 24.31 grams. And then sulfur, we just said, was 32.06. 6 grams. And then oxygen is 4 times 16.00 grams. And so when you do all that, you end up with 120.37 grams. Here we go. So we're going to put that up here, 120.37 grams. We have 3 significant figures to start with, so our answer has to be in 3 significant figures. And so that's going to be, we're going to get rid of these, just multiply across, take 3 significant figures, and that gives you your mass of magnesium sulfate. This is very important information. We're going to be using this in some very practical ways. You know that. Okay. On number 6, it says, how many atoms are in 100 grams of lithium? What do you have to do to tell how many atoms are in 100 grams of lithium? You got to convert to moles, right? To figure out the number of atoms or the number of moles, you got to convert, the number of atoms or number of molecules, you've got to convert to moles, don't you? So you're just going to take your 100, keep trying. Take your 100, yeah, okay. Okay, let's just get rid of that one. Okay, that way I won't get confused. So we got 100 grams of lithium, and I bet my significant figures are off. Don't do what I just did. Make sure you've got the right number of significant figures. We want to know how many atoms exist in that, so we got to go to moles. So we're going to go to moles of lithium. This is the little trick, and I'm going to show it to you here. Are we done yet? No, because we want to know how many atoms there are, right? And this tells me how many moles. So I'm going to go times line, and I'm going to put this down here, moles of lithium, and I'm going to go, can I go from moles to atoms of lithium? Absolutely, can I? Right? So I know in 1 mole of this, I look on my chart, and it's going to give me 6.94. And then I know that in every 1 mole, I have 6.02 times 10 to the 23rd atoms, don't I? Make sure this works. This cancels correctly. And then your numbers are in the right places if you're going to do this. Okay? But you cut out a step, didn't you? All right, and so we have 3 significant figures and 3 here, so this limits our answer. So our answer is going to be 8.67 times 10 to the 24th, and this is atoms of lithium. Okay? Did that really freak anybody out, or is everybody okay with that? Okay. Now, the next one says how many molecules exist in 50 grams of phosphorus trihydride. And you would do it the same way. The only difference is you would add up, for this number, you would add up the phosphorus and then 3 times the hydrogen, 1.01 times 3. And then you would just plug that in there. Okay, number 8. Yes, sir?
Would there be an additional 0 at the end of the number?
Did I... On this one or the next one?
This one.
On number 7?
Yes, because you started with 100 point.
No, this limited it.
Okay.
That's a very good question. That's a very good question. Because I started with 4 significant figures, but this limited me to 3 significant figures, didn't it? And when you multiply or divide, you can't go more than what the least number of significant figures is in what you're dividing. And this came right off the chart, so that's got 3 significant figures. Yes, sir.
The 6.02 times 10 to the 23rd is also going to limit it, correct?
Yeah, that's absolutely, because that's got 3 significant figures. I think I already told you we had it memorized to 4. We were at 6.02 times 10 to the 6.023 times 10 to the 23rd. Just let it go. But that's what they did to us in college. So anyway, but yes, you're right. You have twice there things to limit it to 3 significant figures. Okay. Let's see. So then we're going on to number 8. A chemist has 1.0 times 10 to the 22nd molecules of water. How many moles is that? Okay, so let's write down the given. So we have 1.0 times 10 to the 22nd molecules of water. Okay, and we want to know how many moles that is. Well, I'm going to go times line. I know this goes down here because it's already up there. And I can get directly from this to the moles of water, can't I? Because I know that in every 1 mole of water, there's 6.02 times 10 to the 23rd molecules of water, correct? So I can do that straight across the board. And so that gives me 0.017. Oh, I can't. Yeah, 2 significant figures. There's 2 here. There's 3 here, but I can only keep 2 of them. And that is moles of water. And then it asks me how many grams that is. I'm going to put it back over here so you can see it. 0.017 moles of water times line. Moles of water. I'm trying to get to grams of water. I know that in every 1 mole, there's 18.02 grams of water, because we've done it several times. And so that's going to give me 2 significant figures, 0.31 grams of water. Okay, let's see. The next one. Here we go. The hydrate of magnesium sulfate has 7 water molecules for every magnesium sulfate molecule. Write the chemical formula of the hydrated magnesium sulfate and write the one for the anhydrous. So the hydrated magnesium sulfate, it told us there were 7 waters, so you would just go like that. Okay? And then the anhydrous would just be that without the waters. That's it. That's the easiest thing on your test. Don't miss that. Okay. And then number 10, it says, suppose a student had 100 grams of anhydrous magnesium sulfate, described in 9. How many grams of water could it absorb? Okay, so we have 100 grams of magnesium sulfate. We don't want to know how much water it could absorb. Well, guys, we're actually going to have to go through the moles, aren't we? Because we know for every mole of magnesium sulfate, there's 7 moles of water, don't we? Right? So we have to take this and we have to go to the moles. Guys, if you're in doubt, go to the moles. That's really what it gets down to. So 1 mole of magnesium sulfate, if you add it up, let's see, it is 120.37. 120.37. okay? And so that's going to give us, in 4 significant figures, 0.8308 moles. If any of this is wrong, you got to tell me, because I actually did this yesterday. And that's not that neat, I guess is the word I'm looking for. Now we have how many moles? We know that there is a ratio of 1 to 7 here. So we're going to go ahead and take that number and multiply it by 7, and that's how many moles of water it can absorb, right? So if we take this number and multiply it by 7, it's going to give us 5.816 moles. That's how much water that this can absorb. But he wants it in grams. And so you would just take this and you would go to grams. You would go like this. Grams of water. So it's 1 mole, 18.02. And so 4 significant figures, that's going to end up giving you 104.8 grams of water. So 100 grams of magnesium sulfate can absorb 104.8 grams of water. How we doing? You guys tracking? Can you do it without watching me? That's the important part. Not yet. Okay, no. That's fair. That's fair. Okay, so what I'm going to suggest, did I do something wrong?
Do you have the correct numbers?
4.
2.02, yeah.
Yep, it's up there. It's okay. Let me just say this. I'm just like you. So what you have to do is you have to do every problem until you start memorizing the pattern, okay? And he tells you that there are additional problems that you can work on his website. And I would suggest that if you're struggling at all, to go to the website and do some of those additional problems. And when you feel proficient at doing them, that's when you take your test. That's how I did math, and that's how I did chemistry. And I'll be honest with you, in college, I did not understand chemistry like I do now, but I had an A average, because I worked every problem I could get my hands on until I could see the pattern and know that I was doing it correctly. I'm trying to explain it to you as I'm teaching you the pattern, and really it's a bunch of relationships, isn't it? Okay, it really is. But then I'm trying to give you the way to not have to really understand it to still be able to answer it, right? If you just know where you're starting and where you're going to, then you can step by step take it and add the numbers as you go. That's how I do it. But I figured out that's how I do life, and it drives some of my kids crazy. Because I literally do everything in my life that way. And my kids are like, Mom, you have to have it all figured out before you step forward on projects. I'm like, no, you don't. All you got to have is the next step. And once you get that step, then you figure out what you need and you get the next step. And then you get the next step. That's how, do you see what I'm saying? And it drives my kids nuts. But do you know what? Spiritually, that's what God's taught me. Does he show you what's down the road 20 years? No. He says, you obey me right now, I'm going to shine a light right there. Right? And then you obey me right now, I'm going to shine another light right there. Right there. Right there. Right? You know why? We'd freak out if we knew what he had in mind. Plus, we wouldn't learn all the stuff we're supposed to, correct? So I'm not saying my kid's wrong. My kids are adults now, so they can do what they want to do. But I'm telling you, this is how I actually function in life. So this is how my mind processes. So if you don't get this, but you understand Jay Wiles, praise the Lord. That's great. If you're more like me, this will work. Okay, just practice like crazy. Yes,
You
sir.
can take the test. Are we allowed to have like steps? Like we write down the steps on
You're
top?
not supposed to. But let me say this. Ask your parents, because it's ultimately up to your parents. If you can do it without looking, then you get an honors credit for this class. If you need to look, with your parents' permission though, please, only with your parents' permission. But if you need to look, you can still get your chemistry credit. It just won't be an honors credit, okay?
What would they say in a college?
No, you would not be able to look at, sweetie, you're lucky to carry your pencils and your calculator and get out with your skin. That's how I always felt, at least. So, yeah. So it's up to you. I mean, but Also, college is twice as fast. Whatever we cover this year, you would cover in one semester in college. And that's why it's so important to do this in high school, so that you've got a feel for it, because then you're allowing your mind to absorb it more quick, over a longer period of time. And that's why any of you that have to take calculus, I'm going to seriously suggest you take calculus for the first time in high school, not even dual enrolled. Take it in high school if there's any way you can, because I had a year to absorb calculus. So when I went to college and it was twice as fast, I looked brilliant because I'd already spent a year learning it, so it wasn't that big a deal for me to get an A average in there. But if I had to just do that all like physics, I never had physics in high school, so by the time I saw physics, I'm like, slow it down, you know what I mean? It's just so fast. That's the point. So if you know you're going to be like an engineer or something, I would seriously suggest you find a calculus that you can take before you get to college, so that it's slower, so that you actually get a good foundation, because you really need a good foundation. And they're trying to weed people out, guys. They're trying to get rid of people. They're not worried about teaching you, at least not at the universities in those classes. If you go to some of the community colleges, you have a better chance of getting a teacher that actually wants to teach you the weed out. Let's see, number 11. If the anhydrous form of cobalt chloride absorbs water to become the hydrated form, is that a chemical or a physical change? That is a physical change, because it's still cobalt chloride. It just is now associated itself with the water. Physical change. Number 12, the formation reaction for methanol is given below. If you want to make 100 moles of methanol, how many moles of hydrogen would you need? How many moles of oxygen would you need? Okay, so we have our problem as balanced chemical equation is given to you. Please be aware, he could have just given you methanol and told you to do the formation reaction. Then you would have had to balance it yourself, right? And you could do that. I know you can. You did it in the last chapter. Anyway, so here's our balanced chemical equation. We started with 100 moles as far as our given information. We start with 100 moles of this, and we want to know how many moles of hydrogen do we need, and we also are asked how many moles of oxygen do we need. All right, so let's do the hydrogen first. We always start where our numbers are and drive to where our question mark is. So we're going to write our given again, 100 moles of methanol. Okay, times line. Whatever's here always goes here. And now we're trying to get, let's go to hydrogen first. So moles of H2 equals, okay. Now we can do that because we're allowed. This is legal. We go up here to find what goes in here, and it's a 2. You use your stoichiometric coefficients, and then there's a 4 here, so we're going to put a 4 here. And so that's going to give us, in 4 significant figures, 200 moles of hydrogen. Okay, and so now let's do the oxygen. So we're going to take our 100 moles again. I'm just going to put it down here. Now, you know what? For speed, I'm going to go like this, and I'm going to go like this. Okay, now we're going to do oxygen. So we're going to do moles of O2. The 2 always goes there if that's the stoichiometric coefficient in this particular balanced chemical equation. But here we got a 1 this time, so we're going to do half of that. We need 50 in 4 significant figures, and so it's going to be that, because that's going to cancel. 50 in 4 significant figures, moles of oxygen. Hopefully you can follow that logic. If you're having trouble with that, go back and do some more problems, because this is basic to all chemistry. You have to be able to do stoichiometry. It's not hard, just practice it and you'll start to see it. Okay, number 12. A chemist makes methanol according to the equation given in problem 12. She starts with 24 grams of carbon, 10 grams of hydrogen, and 40 grams of oxygen. In the end, she makes methanol, but there are 2 grams of hydrogen and 8 grams of oxygen left over. What was the limiting reactant? Well, there's no calculations needed there. The thing that you don't have any leftovers of would be the limiting reactant. Excuse me. And because we had leftovers in hydrogen and oxygen, we know that carbon had to be the limiting reactant because it was used completely up. Aren't you glad? No calculations for that one. Number 14, a chemist is making dihydrogen tetrafluoride according to the following chemical equation, and it gives you a balanced equation. If he adds 150 moles of the fluorine gas to excess ammonia gas, how many moles of dihydrogen tetrafluoride gas will be made? So this is very similar to problem number 12 that we did. So we have this equation. That's a 3. Yields. That's going to bother me, so I'm going to fix it. There we go. Plus 6HF. First, I want to make sure that I have it all written correctly, and it's very important. Now, we were given 100, and I'm going to put it over it so that we have more room to work. We have 150 moles of that. We have excess of this. We need to know how many moles of this we are going to make. So we start where we have numbers, and we're going to drive to where we have a question mark. Whatever's here always goes on the bottom. And then we're going to do moles of N2H4 on the top. The stoichiometric coefficient goes in front of it. Here is a 1. So that's going to give us 30 in 4 significant figures. Yeah, because we have 4 significant figures here. So, did I write that? Oh, I caught myself. You guys have been sitting there watching me thinking, she's going to catch that eventually. This is written like this, isn't it? So this is written like this. So now I have to write 30 because 150 divided by 5 is going to be 30, and 30 is in 2 significant figures. So I showed you a trick in class that they do in college that if you put the decimal there, that shows you that 30 is in 2 significant figures. And you are welcome to do that. So make sure your mom knows. You can let her watch this part if you need to. I'll mention it in the test though. Or you could have written it this way, which is what Jay Wiles would prefer you to do. And so you're going to have to find out when you go to college which way they want you to do it. Either way, though, would be 30 in 2 significant figures. But make sure that you didn't just write 30. If you did, your significant figures are off, and you're going to have to take off a point if you're on a test, maybe even more than that. So make sure you watch your significant figures. And see, the reason I knew I wrote it wrong was when I looked at my answer that I have written from my work in the book, I saw that it was 30 in 2 significant figures, and I'm thinking, how could that be if I started with 4 significant figures? So frequently your own work will help you to find your mistakes if you watch closely. And you are supposed to be using the answer key as you do these problems to check yourself to see, wow, where did I mess that up? So, it's better to do that. Let's go to the next one, 15. Considering the following reaction, and has the reaction, we have 150 moles of sodium hydroxide are added to excess aluminum. How many grams of sodium that? Na3AlO3. I'm going to say that's sodium aluminum oxate, but I'm not sure, so please forgive me if I'm wrong. Anyway, so let's go ahead and do this. So we have 6 sodium hydroxide, and then we are going over here. So I'm going to go like this just for speed. And then over on the right-hand side, we have 2 sodium 3AlO3. And we don't need the hydrogen right now, so I'm going to plus, neat. I should have put a plus sign here. Okay, there you go. That's the parts we need. And so we're going to go ahead and start with the 150. Let's get the right number of significant figures this time. Yep, there it is, 150 moles. And here we want to know how many grams. Okay, got an extra step going on here. How many grams of the product that we'll be making? So we're going to start with where we have numbers times line. Whatever's here goes down here. Make sure that you're writing your sodium hydroxide with it, because you can go from moles to moles. That's no problem. And we're going to need to do that, aren't we? Because we're trying to go from here to here. So we can go to the moles of this product. We can't go to the grams, not from the moles of that. We can only go to the grams from moles of this. So that's what we're going to find first. Now we look at the stoichiometric coefficients, and 6 is with sodium hydroxide, and 2 is with this product. And so this will cancel. We have 4 significant figures. 150 divided by 3 is going to be 50 moles of the product. And then we want to take that to grams. So I'm going to go, I'm not going to be able to fit it here, so I'm going to put it back over here. Okay, we have moles of this product to the grams of this product. We know that in 1 mole, now we're going to go and we're going to look up sodium. And sodium is going to be 3 times 22. 3 times 22.99 plus aluminum, which is 2698. And 3 times oxygen, which is 16. And so when we do all that, what we end up getting is 143.95. So I'm going to put it up here, 143.95. And that's right number of significant figures, because you're going to go to the 10th place. And so what we end up getting from all that in 4 significant figures is 7,198 grams of that particular product when we start with 150 moles of sodium hydroxide. It's very important that you keep these with you so that you see what you're doing is legal. You're allowed to do moles to grams of the same thing. You're allowed to do moles to moles when you're doing things within the balanced chemical equation. But you can't jump right from the moles to the grams of something. Okay, we are on number 16. How many moles of sodium would be needed to make 500 grams of sodium sulfide according to the following equation? So we have 16 sodiums plus there we go. And so we were asked how many moles of sodium would be needed to make 500 grams. Check and make sure I have my significant figures right. Okay, looks good. All right, so we are going to start with where the number is. we know we're going to have to go to moles so we can get from here to here. So we're going to go like this. Whatever's here always has to go here, otherwise it's not going to cancel. And we will go to the moles of that. Okay, we know that every 1 mole of that, we look for sodium in our chart. Sodium is 2299. There's 2 of them. And then sulfur is 3206. Hopefully you guys have got this now. I don't want to keep doing these with you. I think you can follow this at this point. It's 78.04. So we're going to put 78.04 in here. Okay. And so that's going to give us 4 significant figures. So 6.407 moles, this leaves, of sodium sulfide. Now, we've gotten from here to the moles of this. Now we can go across to this, can't we? So I'm going to go like that. And whatever's here has to go down here. And wherever we're trying to get to goes on the top, which in this case we're going to sodium. And so the sodium has a 16 next to it, so we put the 16 here. This has an 8 next to it, so we're going to put that there. So it's going to be 2 times this number. We have 4 significant figures, and so that's going to be 12.81. Oh yeah, because it's times 2. 12.81 moles of sodium. Yeah, because this is really 2, so we're just multiplying that by 2. 12.81 moles of sodium. So that answered our question. Okay, number 17. Suppose a chemist wants to make the sodium sulfide in the previous problem. According to the equation in problem 16, she adds 15 moles of sodium to 1 mole of the sulfur, which is the limiting reagent. Okay, let me just put this back, this part. Whoop. There's an 8 involved, but not yet. Here we go. And then we'll just go like that. Okay, we're looking for the limiting reactant, and if we started with 15 moles of this, and we have 1 mole of this, which one is the limiting reactant? You're going to ask yourself, which one are you going to run out of first? Well, you see that every 1 mole of this, it takes 16 of that, and here you only have 15 moles, so you're going to run out of sodium first, aren't you? Anybody that's ever baked cookies and run out of the butter or the chips knows all about that. So the answer would be the sodium. But you see how you would figure that out. You just look, this is a 1 to 16 relationship, and you've got 1 to 15. This one's going to run out first. Then we are up to 18. A chemist is using the following reaction to make boron. If he makes 125 grams of boron, how many grams of magnesium will he need? So we finally get to the whole thing, grams to grams. Okay, let's see. The given information, 125 grams of boron in 3 significant figures. How many grams of magnesium will be needed? There we go. So now we have our balanced chemical equation. Make sure you've written it correctly. You put in your given and your get to. You start where your given is. So we have 125 grams of boron. And we know to get from here to here, we can only go through the moles, the mole tunnel. So we're going to have to get this to the moles. Well, that's not hard. Whatever's here goes here. And now you're going to put the moles in here. Now, I taught you in class how to do this in one big form. So we're not going to put numbers in yet. We're going to go like this. Now we're to the moles of this. We want to get from the moles of this to the moles of this. So whatever's here goes here. And now we're trying to get over here. Okay, so now we've gone from the grams to the moles, moles to moles. Now we need to go from moles to grams. So whatever's here goes down here. And now we can go to the grams up here. Okay, now we can put in our numbers. We know for every 1 mole of boron, we look on our periodic chart, it tells us there's 10.81 grams. Here we look to our stoichiometric coefficients to put in our numbers there. With every 1 mole of magnesium, we go back to our chart and we have 24.31 grams. Now, we have 3 significant figures is going to limit us because there's 4 there and there's 4 there. So the 3 significant figures, let's make sure this cancels, this cancels, this cancels. Good, we're left with what we need. And so when we do all that, we end up with 423 grams of magnesium. Now, I did that in one step. And I told you guys in class that sometimes the digits will be slightly different if you do it in one step instead of taking the significant figures at the end of each step, which is how he did it, and that's fine. This is how I was taught to do it in college, so I'm showing you this way. But if you want, you can do this step by step. Do this and you'll find the moles of, if you do this, you'll find the moles of boron. And then you take that and you go to the next step and you find the moles of magnesium, and then you take that to the grams of magnesium because that's what you were looking for. So you can do it step by step or do it all this way. Your choice. That is how they do it in college, though. Oh, let's see. We just did that one, so number 19. A student is making iron chloride according to this reaction, and it gives it. If he adds 50 grams of chlorine to excess iron, how many grams of iron chloride will he make? How many grams of iron actually react with the chlorine? Okay, so first let's put our problem on here. There's our problem. And we are given, he adds 50 grams of chlorine to excess iron. How many grams of this will he make? Let's start there. So, and then we're going to figure out how many grams of iron he actually used. But let's start there because I don't want too many question marks here. So we're going to start where the numbers are, and we're going to drive to where our question mark is. So we start here, and I have the right number of significant figures, correct? Yes, okay. Times line. So we go grams of chlorine to moles of chlorine, because as long as I've got the same guy top and bottom, I can do grams to moles or moles to grams. Then I want to go across the mole tunnel or across the mole bridge. So I'm going to do another times line, put this down here, and now I'm going to go over to here. Then I need to get to the grams of that, so I'm going to put this down here, and I'm going to go to the grams, which is where I'm trying to go. Okay? All right, now let's go back and put it in. We have one of these. We look at the mass of chlorine. It's 35.45. So when we multiply that by 2, we are going to end up getting right around 70. Yep, 70.90. Then to get this, we look at the stoichiometric coefficients. And then for every 1 mole of this, we look up iron. We multiply chlorine by 3, and we end up getting 162.20. And now we've got everything in place, so we're going to cancel, make sure everything's lined up correctly. We have 3 significant figures to start with, so we're going to have an answer with 3 significant figures, which is going to be 76.2 grams of iron chloride. I'm going to get over here so I can get out of your way. 76.2 grams of iron chloride. Now, we were asked how much iron did we use? And so to do that, let's go ahead and, well, had we done this in steps, we'd have found that the moles of chlorine, which is what we got to here, is 0.705 moles of chlorine. So if we'd have done just this step, this would give us this answer. So now we can go to the moles of iron, because now we're looking for how many grams of this. We could go to the moles of iron, and we have 3 of the chlorine to every 2 of the iron, and then we could go from the moles of the iron to the grams of the iron, and for every 1 mole of iron, and if you look it up, it's 55.85. There we go. We start with 3 significant figures, actually because that's where we started from the whole problem. So we're going to end with 3 significant figures. We actually used 26.2 grams of iron when we used 50 grams of the chlorine to start with. And so there we've answered both of those questions. Over here. Okay, 20. We are running the following chemical reaction, and I am going to cheat because of time, and I'm going to go FeC2O7 plus, that's a 7, plus ... yields ... plus, and actually you could, as long as you can answer the question, yes. But be careful to copy it perfectly, because otherwise everything else will be wrong. Okay, so I've got the thing which is going to be my given, and I got the thing which is going to be my get to. So I'm going to write my given here, and he gives us 115 grams of this, and then our get to is over here, and I need to know how many grams of that, correct? So we know we start where there's numbers, so I'm going to go 115 grams of, that's iron dichromate, I'm pretty sure. 7, that's a 7, believe it or not. Okay, times line. Now I know I can't go from grams to grams, and I also know whatever's here has to go here. So I'm going to put that in first because I don't even have to think about that, right? There's an R there. 7. Okay. And I know I have to go from this to moles of this. It's the only way I can do this, correct? So I got to have the same guy here. Okay. So I know this gets a 1, and you're going to add these bad boys up, and it's going to end up giving you a big number, 271.85. Now, I'm going to show you the condensed way, okay? I'm now at the moles, correct? I know I have to get across the mole bridge, so I'm going to go like this. Whatever's here has to go here. You asked for it, I'm showing you. And I'm going here, so I'm going to go to moles of this. Okay, I'm not even going to put numbers in yet. This has to go here. Now I can go to the grams of that, can't I? Now you can go back in and find out all your numbers. Make sure your bridge is right. This leaves, this leaves, this leaves. This is legal, this is legal, this is legal. Okay, put your numbers in. We look at this. It's got an 8. We look at this, it's got a 4. We know that in 1 mole of this, and we're going to add this up, we're going to go 2 times whatever potassium is, plus chromate, plus 4 times 16. It's going to give me 194.20. Okay. Now, we've got 3 significant figures here. We've got more every place else. So our answer is going to be in 3 significant figures. Now, I'm going to tell you something right now. Okay, the answer is 164, right? 164 grams of this, but I want to try something. That answer is predicated on the idea that you took this step by step. So let me try this. Divided by 271.85 equals, times 2 equals, divided by 194.2 equals, wow, I got some weird number. Divided by 271.85 equals, times 2 equals, times 194.2 equals. Okay. Oh, I did get the same number. Let me say this. If you choose to do it this way, your number may be slightly different than his number. If you show me all the work and you have the right number of significant figures, you will get full credit. The reason why it might vary slightly is because he has you taking significant figures after each step, so you're rounding sometimes, where if you put it all in at once, you're not rounding. Okay? So sometimes it will vary slightly. I don't care about it. That's how you do it in college. Okay? This is how you do it in college. So that's why I would love it if you would learn this way.